All right, so look at this PLS, guys. The purpose of writing it the way I've done is to show that when we try to factor a polynomial, our rational zeros theorem that we've been talking about says that the coefficients have to be what thing? Again? Close. Not real numbers. Not rationals. They have to be integers. Okay? Which are your positive and negative, it's your whole numbers and their opposites, right? Okay, so we need integers. Right now we don't have integers, right? We have rational coefficients, okay? But every time that this occurs, okay, we should be able to do something that changes the polynomial so that it does have integer coefficients, okay? Now, the process is just to factor out a GCF, but I don't even know if I call it a GCF because it might not be, you know, when I say GCF, a lot of us think like a whole number factor, right? Okay, or an integer factor, where here it's going to be more of a rational factor, and it's probably not going to be all that common to see, okay? Do you see a 1/2 inside that -3 as a factor? Okay, so if you do, great. When I look at it, I don't. Okay, I don't see that I should factor out a 1/2 here. So this is what process I use. I'm not saying it's the best way. I'm not saying it's the only way, but it works. Okay, I'm going to multiply by an LCD. Okay, so if I look through that, and it's the reason why I've got, you know, some of them as fractions, some of them as decimal, because I want you to see that this works, that it's true if you've got decimals, and it works if they're written as fractions. So multiplying by an LCD. If I double everything, do all of my coefficients change to integers? Okay, so that's kind of what we got to think. What do I need to multiply by so that everything changes to integers? So I'll multiply everything by 2. So if I do that, now think about this. Multiply everything by 2 gives me x to the 4th plus 3x cubed minus 3x squared minus 11x minus 6, right? Did that change the function? Is that blue function doing something differently than that first one? It has the same zeros. That's something to think about. It will have the same zeros, but does it have the same y-intercept? No, it has different y-intercepts. So does that tell me that it's a different function? Okay, I don't want to do that. I don't want, if I'm going to try to graph this function, I don't want to manipulate it to the point in which it becomes something different and then graph that different thing. Does that make sense? Okay? So just because we multiplied by 2, we've actually stretched this thing vertically now by 2. Okay? I don't want to do that. So when I multiply the right-hand side by 2, I need to multiply the left-hand side by 2. Does that make sense? Okay. Now, if I do that, I still don't want to graph 2 p of x's. I want to graph 1 p of x. So what can I do to get that p of x all by itself? Okay, good. Okay. So you can either divide by 2. If I divide by 2, that's just going to give me back to what I started with, right? Okay, so now you said multiply by 1/2. And I'm not going to distribute that 1. So I multiply by 1/2 here, multiply over here by 1/2. I'm not going to distribute. I'm just going to leave it as that implied multiplication. And now that thing in the parentheses can be factored using our P over Q process. And that will ultimately then be the same polynomial as what we started with. Does that make sense? Okay. Now, the reason I do it that way is because what happens if, you know, right here with the 1/2, it's kind of a, maybe something that some of you can see that 1/2 was a common value that could be divided out of all these to produce then integers, okay? But that's not always going to be the case. You're not always going to be able to see right away, oh, I should pull 1/2 out of everything, and that will divide my coefficients so they become integers, okay? That process, multiplying both sides by an LCD, Okay, and then multiplying by the reciprocal of that LCD to get to be 1px. We'll effectively put that 1/2 where it needs to be. Is it okay? If we go through all the kind of characteristics that we talked about last week, okay? I want to talk about the possible positive zeros, and I want to talk about the possible negative zeros, and I want to talk about the total possible zeros. Okay, so the possible positive zeros, you remember this was Descartes' rule of signs, okay? And it said if you look at your original P of x, now here's the thing. We could either look at the original P of x or we could look at this red one, because the red one, I have not, when I factored out the 1/2, it was a positive 1/2, right? If I factor out a negative 1/2, that would be okay as well, because it's going to still give me the right number of sign changes. So you can look at either one of those to determine your sign changes. But if I'm looking at the red one, it's only the terms that are being summed. Does that make sense? Okay. I'm just going to go back to the top one. How many signs, is that a sign change on the first two? No. Okay, because it's a positive up front, right? So positive to a positive. Now I got positive to a negative. Is that a sign change? Yep, and I got a negative to a negative, and then negative to a negative. So possible number of zeros is equal to the number of sign variations, or that number reduced by an even whole number. Okay, remember this is giving me a quantity of objects, right? Tell me how many positive zeros I have. Well, if I reduce that by 2, I get -1. Can I have a -1 amount of objects? No. Okay, so just one possible positive zero. Okay, possible negative zeros. That is when I take and find P of -x. Okay, so I always find that this, I mean, you could do this a little bit quicker than writing all this stuff out. If I put so basically what we're going to do is go through here and put a -x in all those spots, right? That's why we've talked in the past about how we deal with function notation and how we do the evaluation of functions at different values, because that's what we have to do here, okay? If I plug a -x in right here, what's -x to the 4th going to give me? Positive x to the 4th, right? So positive x to the 4th times a positive 1/2, so it gives me 1/2 x to the 4th, right? Okay. If I plug in a -x right here, what's that going to give me? -x cubed. -x cubed times 3/2 is a -3/2 x cubed. Plug in a -x here. Give me positive x squared, right? Times a -0.5 or 1.5 gives me still -1.5 x squared. -x here. Change this to a what? Positive 11/2. And then that -3, right? So now the possible negative zeros is equivalent to the sign variations up here, or that number reduced by an even whole number. So this is a positive 1/2. That goes to a negative, right? There's 1. That negative then to a negative. Then we got a negative to a positive. So there's 2. We got positive to a negative, so there's 3, right? So we've got 3 possible negative zeros, or reduce that by an even whole number. You're going to have 1. Come on. There we go. Now, if you saw this in your homework did this, but a lot of times when your homework did this, I think that everybody got like one example where this was 1 and this was 1, and then your total possible zeros would be the sum of those, right? It would be 2. This was, I think, at one point, like 0, 2, 4, 6, and then this was 0, so my possibles were 0, 2, 4, 6, okay? Really what happened, my possibles are this one with that one, so I could have 4, or this one with that one, I could have 2, right? Okay? That's really what we're doing, just adding those together to see my possibilities. Now, we also had the mention of last week the upper boundary theorem and the lower boundary theorem, that were things that we decided based on what the last line or the remainder gave us when we did synthetic division. We're going to kind of through the technique that I've told you to kind of get yourself kind of jump started with this by using our technology, is going to kind of bypass that a little bit. Okay, so we might not target that boundary theorem directly in our work now because we're using the graph, the technology to help us get a good starting point. If we weren't allowed to have calculators, and guys, you don't know. I thought when I was in high school, hey, TIA 384, I've used it in 9th grade, 10th grade, 11th grade, 12th grade. This thing must be something that I can take with me everywhere I go. And then I got to college, Calc 1, first day. They said, you got a calculator? We said, yeah. They said, put it in your book bag, never bring it back. Okay? We're allowed to use it. So if I had to do this inside a calculus problem, which is not out of the realm of possibilities. It happens a lot. Yeah, use this process in calculus problems. I don't have a calculator. I don't have any technology. I have to go through these processes. And if I don't use the upper and lower boundary theorem, it might take me 20 minutes to check all my P over Qs. Does that make sense? If I've got tools to help myself out, I'm going to use them. I'm going to let you use technology, but you don't know wherever you go. I mean, and they might take it from you. They might let you use it. You don't. I can find out until you get there. The other kind of features we've talked about, if this is look at that thing right there. Do I know what my end behavior is going to look like? Right, EB for end behavior. As x goes to positive infinity, where is y going to go? Say again? Huh? Infinity, yes. Okay, so when it's the fourth degree polynomial, as x is going to the right, your y values are going up. As x goes to negative infinity, where is y going? Positive infinity again. Okay, so ultimately meaning that every x to the fourth polynomial is going to have end behavior that looks like that, or if it's negative, it'll be the reflection over the x-axis of that, right? So that's not our end behavior. What is our y-intercept? Yeah. Okay. So as an ordered pair, it'd be 0, -3. When you find that by evaluating our P of x at 0, the only thing you'd be left with would be -3 there. How many turning points could you have? And let me write possible turning points. Okay, so turning points, remember, those are your maximum minimums. Those are your extremums, right? Okay, how many can I have here? 3. Okay? If we let n be our leading degree, okay, then the possible turning point is always n minus 1. Okay? So we have 3. All right, now there's, inside that theorem, it says that is at most how many turning points you could have. So you could have less than that. All right? We'll try to discuss it. The more graphs that you see, the more you can kind of say, okay, fourth degree, I could have 3. Can I have 1? Can I have 2? Those kind of things you might be able to eliminate. I think more examples that you see. Okay, start developing those similarity relationships. All right, so how many factors will this thing have? How many? 4. Okay. Be 4 factors. If it's got 4 factors, how many zeros is it going to have? 4. The zeros come from the factors, right? Okay. Now, when I say that, my factors might not be distinct. Okay. I might have x plus 1 4 times. Does that make sense? I might have a multiplicity of something. Okay. If you count those multiplicities, then you will always have as many factors as your leading degree. You'll have as many zeros as your leading degree. Is that all right with everybody? Okay. Those are all questions that I'm going to ask, that we need to ask ourselves every single time we see one of these polynomials. Okay. The hope is that we can do that quickly, though, right? If I want to graph it, we got a lot of junk up there that we can use to graph, right? And a lot of that junk is kind of arbitrary, and we don't know specifics yet. The only way I'm going to know some specifics is if I go through and I start factoring this. Okay? So let's take this red P of x and work through the factoring process of that. Okay? I'm going to erase a little bit of this stuff so I can get some room here. All right, so if I want to factor this, okay, we have to do our P over Q stuff, right? Somebody's been asked, several people have been asking, what are all our factoring techniques? How do I know what to do? Well, you look to see if there's a GCF. That's the first thing to do, always. Factor it out, okay? Second thing, I would look for kind of, depending on the degree, maybe you have, if it's squared, or second degree, maybe you have difference of squares, maybe you have perfect trinomials, that kind of stuff, and some special cases that you can work with. That doesn't work, I try factor by grouping. Can I use factor by grouping here? Factor by grouping, you have to be able to have even number of terms to do it. When I group things, I want like 2 objects in the first group, 2 objects in the second group, right? Okay? Because really, if you think about factor by grouping, the second step of that is always a GCF in regards to our groups, okay? And what will be left over then has to match up, has to be the same. Well, if I have a group of 3 and a group of 2, the leftover will never be the same. So that's not going to help. The next thing, maybe I kind of fall back on formulas, quadratic formulas. Is that going to work here? No. Do I have a cubic formula? We do have a cubic formula, but it's like 3 pages long. Okay, we're not going to use that. So then we get to kind of the catch-all for everything. Okay, so the quadratic formula is the catch-all for factoring any quadratic, right? P over Q, or the rational root theorem, is the catch-all that will factor essentially every other polynomial of higher degree than 2. Does that make sense? Okay. It's not the thing that I would start with. I would never say I'm going to, I got this P of X and it's got 5, 6, 7 terms in it. I might not start right away and seeing if I should just start working with P over Q. I'm going to see if I can make it simpler before I have to fall back into P over Q stuff. Okay. But then we're going to find our values of P, so plus or minus the factors of -6. So those. And then our Q values are the factors of our leading coefficient, which is just 1, so plus or minus 1. So as you're doing this work, I'm just going to, I don't want to rewrite these over again. So aren't my P over Q values just the same thing as P? All right. So here's where I want you guys to use your technology. And really the reason for this, the overall reason is when we get to a test or quiz, I don't want you sitting, if we've got, think about the last test we took, last exam we took, that, and you had 17 questions on it, 15 questions, something like that. 2 hours, do you want to sit, or an hour and a half, do you want to sit with 15 questions to be answered, and you're doing this problem, and it takes you, 25 minutes to do this problem, 10 minutes even to do this problem? You don't want to do that, right? You don't want to chew up time that could be used and applied in better areas, okay? So what I want you guys to do, I want you to take, it doesn't matter which one you do, take the original P of X or take, since we're factoring this one, I would factor this one, okay? Or graph this one, and see where my zeros are. So that's what I've done. I've graphed this. Now you can do this on GeoGebra, you can do it on Desmos, you can do it on your TIA 384. Again, TIA 384 would probably be maybe the last one I use because it's a pain in the butt to see what these zeros are. To be honest with you guys, I think Desmos would actually probably be more appropriate, it's quicker than even GeoGebra. But look at that. Does it give me some starting points? If we understand this whole collective idea of what we're doing here, doesn't it show me that -3 is going to be a 0? So if -3 is a 0, then I know x plus 3 should be a factor, right? So that will allow that x to the 4th to be rewritten. That -1, is that a 0? How many times? Okay, because if I look in conjunction with x to the 4th being my overall rule, then that has to be a double root, correct? Okay. Now, if I didn't have this, if you did not know that was there, if you didn't know what this curve came from, can you 100% tell me that's a double root? No, you just know it's an even root, correct? Okay, or even multiplicity. So that being said, you got to kind of understand that if this was like an x sub 6, and that was the picture I got, because it could happen, okay, then I got to realize that -1 could be, it could show up twice, or it could show up 4 times. Does that make sense? Okay, and if it only shows up twice, then probably the likelihood is that the other 2 zeros that aren't showing up there would be imaginary. Okay, and we'll talk about a little complex a plus bi type thing. And we'll talk about that at some point today. Okay, is that okay with everybody? So we know, at least in this one, because of that restriction of being the 4th, that's 1 0, that's 2 zeros. This would be a 3rd one and a 4th one. Okay, so that's kind of validating all the information we know. So those are starting points. Those are the ones I'm going to do my synthetic division with. Okay, I know they're going to work, right? Now on my test or my quiz, or your test, your quiz, you need to show me the synthetic division. You need to show me you know the work that validates this argument that we're going to make. So when we do synthetic division, I'm going to write my 1, my 3, -3, -11, -6. Okay, and I'm going to put out here in my box one of those zeros. Okay, I think one of them was -3, wasn't it? Okay. Now here's the thing. We've talked about this a lot. This thing is going to factor down to like an x plus, I'm just going to put a, an x plus b, an x plus c, an x plus d. Haven't we had out the discussion you saw on your quiz on Thursday that there could always be some number out here? Let me just call it k. Isn't there always the potential that there'd be a number out here that's going to change ultimately the height of my y values? Okay, so isn't that really what's going on here? Isn't this, so this polynomial here, this x cubed plus 3x cubed minus 3x squared minus 11x minus 6 is going to be factored down to like these 4 black binomials, okay? But there's a k of 1/2 out front, right? So what I guess the argument I'm trying to make here is that when I do my synthetic division, I think most of us are probably going to do it with these, but you can do the synthetic division with this one as well. You can put 1/2 here, you can put 3/2 here, -1.5, -11/2, -3, and go through the synthetic division with -3 here, and you're still going to get a 0 back. Does that make sense? Okay. I think using integers is much easier mental math.
What do you say x cubed plus 3x?
Where?
In the principle.
So, yeah. Sorry. Can I say it that way too?
You said x cubed.
All right, so I do synthetic division with negative, bring my 1 down, multiply, using my 0, multiply, my -3, multiply gives me 9, add gives me -2, multiply gives me +6, right? So this is what I want to see. I want to see that you're able to give me the correct remainder line there to produce essentially what my polynomial p of x looks like when I divide it by x plus 3. And that's what we just did, right? Okay. So I'm going to write down here what p of x is going to look like so far. I know I've got the 1/2 out in front. Okay, that was this 1/2 right here. I now know that it is x plus 3, because this is a -3, so this is the 0 that we checked. We know what the 0 is, we work our way backwards. X minus that will give me my factor. Okay. Now if I just stopped here, what that would mean then is that this remainder here is an x. This was x to the 4th, right? The remainder would be x cubed plus 0x squared minus 3x minus 2. Okay? And really what we're going to do now is regenerate the whole process, but do it with that p of x. Does that make sense? Yeah, or that new polynomial there That is x to the third. That means that might even, I don't know, but I would think that would now, if I just restart the whole process developing new P over Qs, and I could do that process with that one with new P over Qs, that would maybe eliminate some of these 8 P over Qs that I have up here. Does that make sense? So maybe if you don't have technology, that is something to kind of think about. I'm going to keep going. I'm going to try the, what was it, -1. I'll try -1. Bring down my 1, multiply, add, multiply, add, multiply, add, and I get a 0, right? Okay. So -1 is a 0, and x minus that, x minus -1 is also a 0. Okay. All right, everybody? Now, at that stage, you've got options. I apologize for, I wish my smartboard was larger. At this stage, this is x to the what power right here? Second. Can I come up here and say, well, x squared minus x minus 2 is that polynomial? Can you factor that? Yeah, it goes to x minus 2, x plus 1, right? So now you could rewrite this thing here. So x plus 1 as a factor ended up giving me this. And now we know that quadratic factors to x minus 2 and x plus 1. Okay? Or, because you knew, based off your graph already, and I think this would actually be quicker, since you already knew that -1 was going to be a double root, right? Could I really just do -1 real quick? Bring my 1 down, multiply gives me -1, or add gives me -2, positive 2 gives me a 0 right there. And if that was x squared, it's going to be x to the first, right? So now I get x minus 2, and that's where that 0 comes in, or that factor comes into play. But now, we have taken our original P of x, and we factored it. Okay? Now we know where it crossed the x-axis, where its x-intercepts are. We knew the y-intercept. We have a transformation out here, a scalar multiplier of 1/2. Change the y values. We've got a lot of information. We know the end behavior. Does the information here kind of back up the possible zeros idea? Okay? We have 4 possible zeros, right? Okay? Were one of them positive? Was this the only one that was positive? Were the other 3 negative? Okay, so this stuff is validated once we get our P of x, and we look at those things and make sure that all makes sense. Okay. Again, the boundary theorem did not occur here. If this was a negative number, to see if that was a lower, even though it is a lower boundary. Okay, it is definitely a lower boundary. When I look at the remainder line here of 1, 0, negative, negative, 0, it doesn't alternate. Okay, that's what we need is for it to be a lower boundary, right? So even though if it is a lower boundary, does not mean that the remaining line, remainder line is going to alternate. It's not a applied condition. Does that make sense, everybody? Yeah.
So like, if it was alternating and like maybe wasn't when the answers like say something wait for that. So like when you get the alternating, you need nothing is active.
Yes. So let's say I tried like -6. Okay. Obviously, because of the P over Qs, we know that there's nothing to the left. -6 comes to work. But if I want to try -6 and this would go on positive, negative, positive, negative, positive, negative, then I know that there will never be a 0 lower than -6 to the left of -6. Same thing happens with upper bounds, but now if I'm using a positive 0, so there's a positive number in my box, then I'm looking for my remaining line to be all positive numbers. And if that happens, then there will be no value that is a 0 bigger than what was in the box. Again, using the technology to give us a starting point kind of undermines or undercuts that theorem, okay? And you're not going to probably use it unless the only time that you might use that, I think, if I don't let you use your technology, maybe I work out something, okay? And I say this is synthetic division, and I show you the remaining line, and I ask you, give me a piece of information. Tell me something now that you know about the 0 of -3 or that divisor of -3, and you can tell me, oh, it's a lower bound now. Does that make sense? Okay, so it might be a recognition thing that could give you in an assignment. Here's the thing, guys. That's factoring. That is our catch-all for factoring. That might be something I said at the beginning. That might be something you have to do in a calculus question before you can even start doing the calculus. Okay. And the hope is that as we move through the year, we move through the rest of this chapter, we start to get more and more proficient at that. Okay. And obviously, when you get to calculus and you absolutely need it, that necessity will force you to become more efficient with it as well. Does that make sense? This is something that when you get to calculus, I told you this before, you might have homework of 6 questions. And of those 6 questions, the first one you might have to factor by group, the second one you might have to do 18 method, the second one, the third one you might have a special case where it's a difference of squares or a difference of cubes or something like that. And then the next 2 might be you have to address the rational root theorem. Okay? So it kind of hit and miss. Comes back every once in a while. In almost every assignment, maybe you can maybe see this once or twice in a calc class. All right. Into then, guys, the next section, 3.5, which I'm just going to continue. I'm not going to separate the videos here because it would take about 10 minutes to save that one, so we'll just keep going. But 3.5 talks about complex zeros and the fundamental theorem of algebra. Okay. Now it's, honestly, your 3rd year of algebra, and you're now just seeing the fundamental theorem of algebra, which is, it's really not the fundamental theorem of all of algebra. Okay. It's the fundamental. Centuries ago, algebra was kind of focused on just solving equations. Okay. And the theory of equations, and this is fundamental to that process. Okay. It's not fundamental to everything that we've done so far in Algebra 1, Algebra 2, Algebra 3. Okay? The fundamental theorem of algebra is going to be very critical for us in regards to solving a polynomial equation specifically. We need, and I've got it on the board up there, I just want to make sure that we understand this, so I'll show you the kind of the creation of what I've got on the whiteboard. We have had, in the past, we've talked about our real numbers quite a bit, right? Okay. We talked about our real numbers. They are every number on the x-axis that we can imagine. Okay. Meaning that they are the collection of your rational numbers. Okay. So a lot of times when you talk about rational numbers, they use the capital letter Q. Okay. But those are, they use Q because Q sounds like, or starts the word quotient, right? Isn't that what rational numbers are? Is that they're a quotient of 2 numbers? Okay, a ratio of 2 numbers. So we got our rational numbers. Now our irrational numbers as well. So this takes care of everything like 5. Because inside that are your integers. Inside that are your whole numbers. Inside that are your natural numbers, right? Okay. So we can keep going further with that kind of Venn diagram of our rationals. I'm not going to. But we also have then our irrationals, right? So our irrationals, a lot of times, are written that way, where they use a capital Q. Now, they're fancy Qs, they're fancy Rs, that kind of thing. So a lot of times they'll put these like extra bars on them. But then we put that asterisk there, and that just basically tells us it's all the values of our reals that our rationals did not pick up. Okay. So there are things like pi and radical 2 and radical 3 and so forth. Okay? Make sense? All right? We slam those 2 groups of numbers together and we develop our number line. Okay? Our real number line, the x-axis or the y-axis, and every number you can imagine is on there so far. Okay? Every number that we. However, I have to double check my history here, but I believe it's Euler came up with, and he defined it. He was working with basically trying to solve the equation. This is where fundamental theorem of algebra kind of gets its kind of basis, its roots, is that he was interested in solving an equation very similar to x squared plus 1. Very simple equation. And when we take x squared plus 1, our answer is always x equals the square root of negative 1, right? And that was a conundrum. That was a problem. Okay? We didn't have what that was equal to. Okay? So he made the definition, The square root, he defined this. He said the square root of -1 is equal to I, right? Okay? And then we get our imaginary numbers. So I'm going to write pure imaginary, purely imaginary, okay? I'm not going to put a letter we use a lot of times with imaginary numbers and complex numbers is Z. I'm not going to write that, okay? So we got our imaginary numbers, which is a misnomer. It's not that they're like, and I think this is what kind of confuses students sometimes, is that all they're imaginary. They don't really exist like all my friends, right? Okay? They do exist because we define them. They work. And what's nice is it kind of gives you an understanding that, yeah, they solve their solutions to that equation. But when Euler was working on this, was there an application? Was there a real-life application for it? Probably not. Okay? But now that we have electricity, there's a huge application for complex numbers. Okay? Once we now understand like quantum mechanics and quantum physics and all that kind of stuff, there's a huge application for imaginary numbers. Okay? If you go into maybe something you guys understand the resistance and current, I have like a 9-volt battery and a very tiny wire and a light. I could probably light that light up. Okay? But if I have a 9-volt battery and then I have 300 yards of wire between that 9-volt battery and that light, the electricity is going to kind of fade. It's going to die throughout that wire. Does that make sense? Because it's just the resistance of the conductor doesn't allow the electrons to flow. Okay? So that resistance and ohms and that kind of stuff can be explained. And we like to use two numbers to explain it. So imaginary numbers, complex numbers, A plus B, I type things allow us to do that. Okay? That's pretty much all I know about electricity, other than it hurts really bad. But what we do is something similar to what we did with the rational and irrational. We jam those together and said, let's make one group called the reals, right? So now we got our imaginary and we got our reals. We want to jam them together, and we get a group called, okay, so we use a capital C. These are complex numbers, and they're anything of the form A plus BI. Okay? Our imaginaries were anything of the form like I, 2I, 3I, 4I. Just pure imaginary, pure, no A out front, no A plus anything out front. Okay? Now here's the thing. Is 5 complex? Is 5 in that group right there? Yep. Is that group within the complex group? So 5 is complex, right? Because 5 can be written